Okay, welcome everyone. Today we will move on to 1C. There will be an opportunity, I'll pop around, see how we all felt about 1B, make sure we're all pretty comfortable with that. If there's some common questions, we will address them together. Nonetheless, we will today move on to 1C. It is some newish content, so it's stuff we haven't seen before, but using some skills we have developed in the course of Year 11. And the other thing to say about 1C is we don't really need a complete comprehension of 1B to work through 1C. So we can move ahead, and we will. So let's talk about the theory first. The theory that I have is logarithmic functions. So remember, we talked about exponential functions. Those are functions that exhibit exponential growth. It's where we have the form a to the power of x, right? The variable is in the power. Now we're talking about logarithmic functions, which are of the form log of x. Now, if a is the base here of the exponential function, and it's the base of the logarithmic function, these are what we call the inverse of one another. And so you can see, if you look at your diagrams, I've sketched the line y equals x, and they are mirrors of one another. That the exponential function, okay, of 2 to the x is the example that we have here, the graph of 2 to the x. The inverse of it, if you flip it over that line y equals x, you have the function log in base 2 of x. Okay, so that's quite important to know. There's a relationship between 2 to the x and log in base 2 of x. Similarly, okay, in the next one, we've got the graph of e to the x, and then the corresponding inverse function, ln of x. Okay, that's the logarithm in base e of x. They're the inverse functions of one another, and we use ln to get rid of e, we use e to get rid of ln, right? Okay, so our first function here, we've graphed a few exponential functions, but we're going to use some skills that we did on yesterday to solve some of the problems here. So I'm going to be referring to, on the second page, page 13, I've got recall about exponential functions. This is what we did in exercise 1A, and so we're going to answer some of these parts of it today. So our question here, consider the function y equals 5, take 2.4 times e to the x plus 3. Identify the values of a, b, c, and d. So the basic exponential function has the form, how do we describe it? I'll use the same notation, a times b to the x take c plus d. So we're trying to identify what corresponds with a, what corresponds with b, c, and d. Okay, so a does not correspond with 5. Alright, that's a little trick that we put there. Sometimes we will put them in opposite order. A is always the coefficient of the base. That means the number that's multiplying the base. That's what we have to look for. And so A is minus 2.4. We have to consider whether it's positive or negative. A is minus 2.4. That's a dilation factor. So it's dilated by a factor of 2.4. And because it's negative, any negative will always flip a graph upside down. Okay? So just as a really quick example, like if we have y equals 2x squared, okay, the dilation factor is 2, it's stretching 2 units up. If we have y is minus 2x squared, it's going to completely invert it. It flips it upside down. It makes every y value negative, okay? So the 2.4 stretches it by 2.4, the negative is going to flip it upside down. Okay, the base, b is the base. Our base here is e. Alright, e is what, 2.72 approximately. We have c is the horizontal translation. Now, in this circumstance, Harry and Jack, c is, we've got plus 3 here, and I've expressed it as minus c. So I'm going to describe c as minus 3 because it's x take away minus 3 will give me plus 3. X take away minus 3 will give me plus 3, which means the value of d then is just positive 5. Okay, so all we need to do to describe how it affects the function, these affect the shape. And in fact, when we were looking at it in 1A, we were able to describe the shape based on these values. You can go ahead and do that. I said, that's not something we need to know, we can just refer to our calculator. C and D, C affects the horizontal translation. All right, so because we have x plus 3, or because we have minus 3, we're shifting it 3 units to the left. Okay, moves 3 units left. And with positive value of 5, moves the graph 5 units up. Okay, and look, we hit a lot of those kind of skills when we were doing the roller coaster folio, that super fun roller coaster folio that you do in semester 1, only to be topped by the year 12 methods folio that you get to this year, even more fun. So we've got A, B, C, D, that's very good. Let's move on to the second part. Graph the function. So I'm going to bring it up on Desmos here. I'll encourage you guys to bring it up on your calculator because we're going to refer to it. So I'll give you a minute to bring it up. I'll bring it up on Desmos. And my Vivi code is 5196. So graph it, and you're just going to have to try and figure out an appropriate V window. Just set the standard to begin with. So we have 5 take 2.4 times e to the x plus 3. Alright, so in order to sketch that, so if you've set it to standard, it probably looks pretty similar to mine, except my y is not going down very low, so I'll just adjust that a little bit. I'll set my y min as minus, let's go to 10, let's see how that, still can't see it, I'll just, that's 19, let's go for minus 30. No, so it's going to go way down before we get a y-intercept, so that's absolutely fine. Let's give it that an approximate sketch. Okay, so just in order to sketch it, we want to have the shape and any intercepts that are occurring. So we have the x-intercept occurring here at minus 2.26. So I'll go minus 1, minus 2. Here's the x-intercept. Here's minus 3. I'll go down just to y is minus 10 for now, y is positive 10, just put a couple of lots here. And we can start to see a asymptote here, okay? It's approaching some value. Look at that y value, 4.9999999, 4.997, okay? As I move to the left, it's approaching 5. There's an asymptote at y equals 5. So I'll put that in here. Okay, so we can refer to the graph to get the asymptote, but I'll show you the reasoning from it in a moment. And it's not asymptotic there, so I should just demonstrate it's going down that way forever. Whoa. Okay, so we've got an x-intercept. The y-intercept is going to be way down unless we increase our scale a fair bit. We've got the asymptote, and we should just label it as well. So to label the graph, always get in the habit of doing this. State the function, 2.4 e to the x plus 3. Okay, that's especially crucial if you have two functions on the same graph. So we've got a graph, but that'll be fine. Okay, Part C says state the domain and range. Now for this we can refer to the graph to answer it, but let's just flick back a bit to where we've got the recall paragraph stated, and you can see the last two dot points. The domain for all exponential functions, XER. Alright, so for the domain, we will make a statement x belongs to all real numbers. It's going to the left forever, it's going to the right forever, x can take on any value. For the range, we've got the range is going to be, y. Y is less than d, or y is greater than d. Now in this circumstance, it exists for all values less than 5. We can see that from the graph. We can see that because of the shape it takes on, that the range is going to be less than 5. Okay? It exists for every value of y that is less than 5. That's how we answer the domain and the range. Very good. Okay, let's move on to D. We have find the x-intercept exactly. Now, the x-intercept occurs when the y value is 0. You need to remember that. X-intercept when y is 0, y-intercept when x is 0. So, if this is our function, if our function is 5, take 2.4 times e to the x plus 3, and you know how we've got y equals? Well, I'm just putting 0 where the y is, aren't I? I'm making it equal to 0. The x-intercept occurs when the function is 0, when the y value is 0. So that's the equation that we're solving. We're solving 5, take 2.4 e to the x plus 3 equals 0. This is a skill we learned yesterday, okay? So we want to break this down because we want to get the exponent part by itself. The first thing to do, get rid of the 5 by subtracting 5 from both sides. Now, I'll just want to point something out as well. It says, find the x-intercept exactly. Now, this is going to be something we pick on a lot over the Year 12 course, because you could just look at your graph and go, the x-intercept, 2.26. All right, and you say, I've answered the question. No, it says exactly. And so let's go through and I'll show you why that's going to be an exact answer. In our next step, we're going to get rid of this 2.4 by dividing both sides by 2.4. Then we will perform the natural logarithm of both sides. That's good. Now, on the left-hand side, you can think about it in two ways, right? If you want, that x plus 3 can come out the front and you can simplify it like that. But we don't need to, because this is the logarithm in base e and we're asking, we've expressed it as a single power of e. Remember the rule, ln e to the x simplifies to x. Therefore, ln e to the x plus 3 will simplify to x plus 3. Okay, important to put the brackets around it because we've got one more step, which is to subtract 3 from both sides. And we're demonstrating the 3 is not part of the ln, the 3 is out here. We have ln of this part, take away 3. Now remember, there are lots of ways this can be presented. And you will no doubt have found from the exercise yesterday, you have an answer and it doesn't necessarily correspond with the one in the textbook. That's okay. Put the one in the textbook in your calculator, put your answer in your calculator, make sure they're the same. That's how you can confirm it, because there's lots of ways of writing this. For instance, we could split this up, right? If we have ln of a on b, we can write it as ln of a take ln of b. Okay, remember that? So there's lots of ways that these can be presented. We're accepting anything from there onwards, okay? As long as you've shown it exactly, because there's so many possible paths you can take, we're very flexible with what you get out, as long as, what are we looking for? The correct algebraic process. So let's just talk about that one again quickly. We want to get the exponent part by itself before we perform the logarithm. So we break it down like a linear equation. Take 5 from both sides, divide both sides by the minus 2.4, the negative and the negative cancel. All right, so that becomes a positive term. Perform the natural logarithm of both sides. This simplifies to x plus 3, take 3 from both sides. And now this is what we call an exact answer, because the logarithm of 5 on 2.4 is an irrational number. It has an infinite number of decimal places. And so rather than writing an infinite number of decimal places, we can express it like this. And what that means is this answer is exact. It's the exact answer. It includes every possible decimal place that exists after the 2.26 that the calculator's given us. Okay? We've found it exactly. And so whenever you're asked to find something exactly, that means there's an algebraic process required. Absolutely has to be done. Okay, but then if we have a look at E, find the value of x when y is 2.3. All right? It doesn't say exactly, so we don't have to do it using the algebraic process. If we were to do this one algebraically, what are we doing? We're setting y is 2.3. Okay, so let's just restate the function again. 5 take 2.4 is the x plus 3. If we were doing it algebraically, I would put 2.3 where the y is. And I would solve this function just like we've done here. It's very similar. Okay? Subtract 5 from both sides, divide by the negative 2.4, ln of both sides. We're not going to do it exactly. You can if you want. I'm going to get it from my calculator. So you want an x value. It says find the value of x. So you're going to g-solve x calc. I want to know x. I'm doing an x calc when y is 2.3. The other way is to, like I'm going to do a Desmos, sketch the line 2.3. What's the approximate x value? We've got minus 2.882. Simplifies to round to minus 2.888. Okay, so that's a recap. We've done some exponential functions before. All right, let's move on to the logarithmic function. Unless there's anyone want to ask a question about any of that?
Where did you put that into the calculator? Like what?
Yeah, so you graph the function. Yeah, in the graph mode, and go g-solve. Yeah, I might come speak to you about that specifically. Okay, we've got the logarithmic function, question 2. Consider the function log in base 5 of x plus 3, take away 2. Part A says identify the values of A, B, C, and D, and discuss the translations from the base logarithmic function, the base ln function. So, flipping back a couple of pages, that's our new content. That's what's highlighted. We can see the general log function applies to all logarithmic functions is A ln of B, x take C plus D. Let's write that up here. A ln of B of x take C plus D. So we're going what corresponds with A, what corresponds with B, what corresponds with C, what corresponds with D. So A is 1. There's nothing stated out the front, so the coefficient is 1. If it was negative 1, we would put A as negative 1. Okay. B, this number here in front of the bracket, is also 1. C is going to be minus 3 again, because we have minus 3. We'll give you the positive 3 that we're required, and we've got D is minus 2. And again, all we need to state for it is that A and B affect the dilation. So A is from the x-axis, B affects the dilation from the y-axis. That word dilation just means stretching and compressing. Okay, you can think of the pupil dilating. All right, someone's eye. Okay, so these affect the shape. That's all we need to say for now. A is on the vertical axis, B on the horizontal axis. C, we've got minus 3, shifts it 3 units left. And this minus 2 shifts it 2 units down. So that's what A, B, C, and D do. Okay, then we're asked to graph the function. Now, you can graph a logarithm in base 5 on your calculator. I'll just write the process up here. So again, I'll get you guys to do this as well. You go option, calc, log A, B. That's it. Option. So you're in the graph mode, you're ready to type it in. You press option, calc, and then you'll see log AB corresponds with F4. Okay, and you can type in there, you need to make sure the base is 5, the logarithm of base 5. So we have...
Delete all that. You like the log, and then you did log AB.
There we go. Alright, graph it.
He's dead. Yeah.
Yeah. Just stops right in like
It's just a starting point.
starts like minus 25.
And let's get a y instead there. 0 and minus 1.317.
I don't know.
Chill.
I'm drawing my what was it? Log 5.
How does his finish like? Yeah, no.
Okay, I'll just float
Just
quickly. Does anyone have any
stop, yeah.
calculator issues? Someone ask
Yeah.
that? Yep. It won't pop show the whole thing because that's correct. Yep, that's correct. Yep, it will disappear because the calculator's like, oh, I can't load that number because it doesn't exist for negative values. Very good. Negative part 2. That is very good. Very good. Very good. Very good. Yep. Everyone gets the same. Excellent. Well done. So you can see even mine on Desmos, which is a supercomputer, even mine stops as well, doesn't it? Because it doesn't exist past that point. We can't calculate any further values. All right. Okay. Well, let's label the function, I suppose. Label the axes, label the function. The function is logging base 5.
Definitely look that up.
Okay, part C. Everyone okay for part C? With the graph, look, you'll be doing a fair bit of graphing today, so maybe come back to it. Let's have a look at part C. It says state the domain and range. So let's have a look then at the notes that we have for logarithmic functions, the general form for a logarithmic function. We've got A, B, C, and D. We've got comments about the domain and range. Okay? Maybe I can point out as well, C is, so for the third dot point, C is the horizontal translation, and hence x equals C is the vertical asymptote. We identified the value of C here was -3, that the functions would shift to 3 units to the left, and the vertical asymptote is -3. We can see that from our graph. We can understand that because of the function. The value of C will always be the equation of vertical asymptote. Okay? So for the domain, we can see this function exists for all values of x larger than -3. X is larger than -3, so the way we denote that, x is greater than -3. Not greater than or equal to, because it doesn't exist at -3, it gets really close to it, but all values larger than -3. And then for the range, the last dot point, the range for all logarithmic functions is yeah. So remember, logarithmic and exponential are opposite. We saw for an exponential function, the domain was xer. We see for a logarithmic function, the range is yer because it inverts. The inverse of one another. Okay, where are we? Find the y-intercept exactly, okay? So I've stated the y-intercept here. We want to find it exactly. So the y-intercept occurs when x is 0. So if I put x is 0 into this equation, all right? So I'm going to have, this is the function, logging base 5 of x plus 3 take away 2. If I put x is 0, the int, I like to call it, the y-intercept when x is 0, 0 plus 3, and 0 plus 3 is just 3. Logging base 5 of 3, take away 2. All right? And if you put that in your calculator, you know what number you'll get? 1.317. Okay, so that's the x-intercept. That's the y-intercept exactly. That's our y-intercept. Okay, part E. Find the value of x when y is 2.3. All right. Now, we've got two strategies we could do again. We could just use our calculator. We can't see it on our calculator, right? We want to know the value of x when y is 2.3. Let's use the algebraic approach. So we've got y is 2.3, and we're trying to solve this equation for x. This is good because we don't get to solve many logarithmic equations, so it'll be good for us to solve it. So we're solving, we said find the value of x when y is 2.3. So I've set that up. The only thing I'm going to do, I'm going to put the 2.3 over here just because it's my preference to solve x on the left-hand side, whatever, it doesn't make a difference. The first thing we have to do, just like when we're solving an exponential equation, we need to get the exponential part by itself. When we're solving a logarithmic equation, we need to get the logarithmic part by itself. So we need to get rid of this minus 2 first by adding 2 to both sides. Okay, that's the first part. Now, let's take you back to yesterday. And yesterday we talked about, if we have something like this, if we have ln x is 2, we saw the way we get rid of ln x is we raise e to the power of both sides, right? We would go e to the ln x, e to the 2. E to the ln x would simplify to x. All right? E to the ln x simplifies to x. And so let me draw your attention to then how to get rid of logs. Okay, so this is on page 14. How to get rid of logs. Given ln x equals 2, put e to the power of both sides. Given log x is 2, we put 10 to the power of both sides. Why 10? Because the logarithm is base 10. Given log in base 2, put 2 to the power of both sides. Given log in base 3, put 3 to the power of both sides. Here we have log in base 5. What should we put to the power of both sides? 5, okay? So if we put 5 to the power of log in base 5 of x plus 3, and 5 to the power of 4.3, now these logarithm components will cancel, all right? We're left with x plus 3 equals 5 to the power of 4.3, and then to get x by itself, we subtract 3 from both sides. Okay, I'm going to stop there. That's enough to get started on the exercise 1C. There's a lot of graphing in this exercise, and in the textbook it says don't use your calculator. I'm going to encourage you to use your calculator. I want you to be very familiar with it. So yeah, my encouragement is use your calculator to help you out and refer to the dot points as you need. But let's get started there.